All right, let's dive into one of those ideas in calculus that's just absolutely foundational. One-sided limits. This is the tool that lets us get super precise about how functions behave, especially when things get a little weird.
So, think about this for a second. What if you had a function that acts one way if you're coming at it from the left, but acts completely differently if you approach from the right? You've got a single point, but two totally different stories. How on earth do you describe that with math?
You see, the standard limit that you're probably used to is always trying to find a single unified destination. But for these split personality functions, that whole approach just kind of falls apart. The limit might not even exist, or at the very least, you're not getting the full picture. We need a better tool, a more precise one.
And that tool, my friends, is the one-sided limit. This is where, just like it says on the screen, direction changes everything. We're not just taking one road to our destination anymore. We're splitting our approach into two very distinct paths, one from the left and one from the right.
And the difference between them is actually super simple. It's really a tale of two paths. For the left-hand limit, you're only looking at values that are less than your target point A. Just imagine you're on a number line, creeping up on A from the left side. The right-hand limit is the exact opposite. You're only considering values greater than A as you slide in from the right. Now, the notation here is absolutely key. When you see that tiny little superscript minus sign sitting next to the A, it does not mean it's a negative number. Nope. Think of it like a directional signal. It's telling you, hey, we are approaching A strictly from the left, using values smaller than A.
And yeah, you've probably guessed it. The little plus sign means we're doing the same thing, but approaching from the right, using values that are always bigger than A. Getting this notation down is really the first big step to mastering this whole concept.
So why do we even care about splitting things into two separate paths? Well, it's because they have to agree. They have to come together for the regular, old, two-sided limit to even exist. And that brings us to the most important rule we're going to talk about today.
This right here is the golden rule. The most crucial phrase is if and only if. In math, that means this is a two-way street. No exceptions. If the path from the left and the path from the right lead to the exact same value, then congratulations, the general limit exists. But if they lead to two different spots, the general limit simply does not exist. Period. They have to agree.
Okay, enough with the theory. Let's make this real. For our first case study, we're jumping into the world of electrical engineering to look at the Heaviside function. It's basically the perfect mathematical model for a simple on-off switch.
Just look at how simple this definition is. For any time t that's less than 0, the function's value is 0, the switch is off. The very instant time hits 0 and moves past it, boom, the value is instantly 1, the switch is on. There's this sudden, instantaneous jump right at t equals 0.
And this illustrates our rule perfectly. Let's break it down. As we approach 0 from the left, using all those negative time values, the function is always 0. So the left-hand limit is 0. But as we come in from the right, using the positive time values, the function is always 1. So the right-hand limit is 1. And since 0 most definitely does not equal 1, the two sides don't agree. The general limit at t equals 0, it doesn't exist.
So why should you care? Because this jump is the mathematical heart of a digital signal. Think about it. Unlike a smooth, flowing analog wave, all of our digital information, ones and zeros, is built on these sharp, instantaneous steps from off to on. This function is what makes that possible.
For our second case study, let's look at a function that is just fundamental in computer science. It's used for the super simple but absolutely critical task of figuring out if a number is positive or negative.
This is the signum function. The whole trick here is that absolute value on top. Just think it through. If x is a positive number, say 5, you get 5 divided by 5, which is 1. But if x is a negative number, like -3, the absolute value turns it into a positive 3. So you get 3 divided by -3, which is -1. So you can already see the pattern here, can't you? It's the same logic. When we approach 0 from the left side, we're using negative numbers, so the function is always cranking out -1. The left-hand limit is -1. But approach from the right with all the positive numbers, and the function is always spitting out 1. The right-hand limit is 1. Once again, a total disagreement. The general limit does not exist.
And in programming, this is a real game changer. Instead of writing a bunch of messy if-then statements, the signum function gives a computer a super clean, efficient, single operation to check the sign of any number you throw at it.
Okay, for our third and final case study, let's look at something we've all experienced in real life. Costs that suddenly jump. You know, like when you're shipping a package. The price is one thing up to £1, and then it instantly leaps to a higher price the moment you go even a tiny bit over. This behavior is modeled perfectly by the floor function. It sounds fancy, but all it means is round down to the nearest integer. That's it. So the floor of 2.1 is 2. The floor of 2.9 is also 2. It only becomes 3 when you hit exactly 3. On a graph, this creates a cool pattern that looks just like a staircase.
So let's analyze this at any integer. We'll just call it n. As we approach n from the left, with values just a hair under it, like 2.99, the floor is always going to be 1 less than our target. It'll be n minus 1. But the second we cross over n and approach from the right with values like 3.01, the floor immediately jumps up to n itself. And since n minus 1 is never ever going to equal n, the two sides can never agree at any integer.
This is the math that models any kind of tiered pricing system. We're talking postage, shipping rates, even some cell phone data plans, where you get charged for the next whole gigabyte the second you go over your limit. The math of that price jump is captured perfectly by the floor function.
So, we've looked at a digital switch, a sine function, and a staircase cost. After all that, what's the final verdict? Well, it really all comes back to that one single core rule. The two sides have got to agree.
This table really says it all, doesn't it? For the heavy side function, the limits were 0 and 1. For the signum, they were -1 and 1. For the floor function, they were n minus 1 and n. In every single case we looked at, the left-hand limit and the right-hand limit were different. And because of that disagreement, the general two-sided limit simply did not exist.
If you take one thing away from this whole explainer, let it be this. A limit is all about a destination. And for that destination to be valid, it cannot matter which path you take. Whether you come from the left or you come from the right, you have to end up at the exact same spot. So I'll leave you with a question to chew on. Now that you know what to look for, these instant jumps, these step changes where direction is everything, where else do you see them? In economics, in physics, maybe even in your day-to-day life. Trust me, the world is absolutely full of functions with split personalities.